Welcome to the first video of a series I'll make on the Statistics 1B course for the Rijksuniversiteit Groningen, or University of Groningen, put it in English. It's good to be back. Now, this is going to be a special lecture for two reasons. For one, this is going to be a lot longer than usual, because it's not just going to be about the content of the lecture, but also about the content of the course that came before. As you can imagine, Statistics 1B follows from Statistics 1A, and it's useful to know what parts of 1A are especially relevant and what you could expect from it in the new course. Also with regards to what you might get on the exam and what you don't have to expect. Just have a little bit of a better idea of what to expect. And so the second thing that's special is that this particular video, unlike all the others, is going to be public, because I think it's useful information for anyone, even if you're following along with the course and it's going well, which would be terrific. I think that even then it's still useful to know about the first couple of, about how the previous course connects to this one. So that's exactly what you'll get here. First, we'll start off with Statistics 1A, talking about the recap. So to put it very broadly, Statistics 1A had, I think I would like to say, 6 big topics. We learned about descriptive statistics, which was at the very start. So that's what the means, the frequencies, the standard deviations, and how to make graphs out of that. Then we moved on kind of to linear transformations. Wasn't a really big topic, but we did have that. Then we had distributions. So we learned about especially normal distributions and how to calculate the area and how to standardize. But most importantly, we learned how to graph a normal distribution. Then we moved on to associations. That's the third big one. Associations. That was the correlation, regression, Spearman's rho, Kendall's tau. A lot of good stuff. Then we got a little bit about research design. Uh, Especially since you already had research methods, there was probably a lot of overlap in that, like how to sample and how to distribute people among different groups. And then we got to the really hard part of probability theory, and then eventually how to use probability theory to actually calculate probabilities for various distributions and how the sample connects to the population in that regard. Like if you have a known population, then what does the sample look like? Now, with statistics 1B, in general, when you move on to a new statistics course, they're not going to explicitly ask about content from prior courses unless it's explicitly repeated within the lectures. So, for example, but it is still assumed that it is known. So, for example, in statistics 1A, we've technically learned what a mean is or standard deviation is. And in statistics 1B, you'll be using means and standard deviations again. So, in a way, you're still expected to know what is a mean and what is a standard deviation. But there's no chance that they'll have a question where they just give you a bunch of like 10 numbers and ask you what is the standard deviation here, what is the variance here, because that is specifically statistics 1A. Another example, for example, the standardizing, calculating a z-score and finding a corresponding probability in table A, we still need to do that for some parts of statistics 1B. So that's a skill because it's explicitly being repeated. You still need to know how to do it, because you're going to be using exactly those skills to do other things now as part of a bigger, as part of something bigger. Then finally, if you're, for example, regression, that's not at all a part of statistics 1B, not even in any way. You don't need that for statistics 1B. They're not going to ask anything about regression. Now, statistics 2, that's a different thing. That's next year in September. Then you'll definitely need regression and correlation again. But for now, for statistics 1b, there won't be any questions on that. Like it's not part of the course, nor is it related to anything that's in the course. So in that regard, just to make a little bit of an overview on that. So descriptive statistics, it's mostly, well, you still need to know how to interpret graphs and means, just how they work, but that's probably not the part that a lot of people struggle with, so that's good. Distributions are again necessary because of what we'll be focusing on. So you still need to know a lot about normal distributions, how to check for normal distributions through plots, so those things especially. So it's a little bit of the foundation of what we'll be talking about. Associations, you can just forget about completely. There's nothing correlations, nothing about regression, Spearman's row candle style, not in this course. Research design also wasn't a big topic, but also not going to be any questions on that. Probability theory, technically we're using some of the rules implicitly, but none of that PA times PB and PA or B and PA, nothing like that. None of that is going to appear on this exam. And finally, the final part where it was about calculating the probability of getting sample outputs given a particular population. That is by far the most important part. So not the binomial part, that is part of it, but we don't really repeat that either, even though they do have it in the reading list, which is a bit odd, but they never talk about it. It's a bit vague. But the big focus, at least, is especially on what lecture 12 was, which was the sampling distribution. So most of it was really like the last couple of lectures where most of the relevant information comes from. So that's also what I want to repeat here. Over the course, we learned that there were 3 types of distributions that are relevant to us. We have a population distribution. That's just how the scores are distributed in the entire population. Of course, we can take a sample from the population. And then we have a sample distribution. And we learned in the very end of the course that we also could have something called a sampling distribution, which is something different. So it's a distribution of sample means. So just as an example, this is just all simulated data. I made a data set with 100,000 people in it with a mean of 100 and a standard deviation of 15. Now, as you can see, due to randomness, it's not exactly that, but it's 99.9 and 14.998, so close enough. That's going to be our population. We have 100,000 people. We're having IQ scores, and they follow the normal distribution perfectly for convenience. Now, what we can do is we can take samples from it, and this in this case is a sample with 100 people. Here are 4 samples, and what's important to note that the sample, as we know, it's not going to be exactly the same as the population. So the population was exactly 115, 100 mean, standard deviation 15, but the sample is a little bit different. Now, of course, this isn't weird. This is pretty close, actually. Oh, this also. See, samples can be pretty good. But this is the most different one, actually. But this is what we know from samples. If we take a sample, then it's not going to be exactly the same as the population, but it's going to be something relatively close. And that's also what we see here. We take a sample of 100. Another thing is the population is pretty much perfectly normally distributed. It follows the curve beautifully. The samples, not quite, but close enough. Like, first, this is a weird dip here. This is a bit flat. This feels a bit skewed. Again, they're not perfect, but this is also to show that if you take a sample from a population distribution, that the individual sample isn't quite perfect. And that's also not a problem, by the way. Like these minor deviations from it, these do not raise any alarm. Also, not really any outliers, so all good. This is a little bit different. What this does is, what this distribution mirrored is that we took 100,000 samples where each of them had a sample size of, was it 100? Did I do 100 or did I do 80? I think I did 80. Otherwise the result's so weird. Yeah, I didn't do 100, I did 80. Either way, what the point here is, the sampling distribution answers the hypothetical question. If I were to take, in this case, 100,000 samples, just to have a really big number, because that's the idea. If I were to take 100,000 samples and I were to record the sample mean for each of them, how would the sample means be distributed? And what you'd expect is that the population mean is going to be the same as the mean here, that the standard deviation is going to be a lot smaller, because of course, if you have a mean of, for example, 80 people, if you have a mean of 80 people, then it's fair to assume that that's going to be a lot less variable than if you take individual outcomes. And it's going to be normally distributed, more normally distributed. Those were the lessons we learned in Statistics 1A near the end, where we learned how to calculate this distribution before we even actually had to do the samples. Assuming that you have this information of the population, you can use that information to estimate what this distribution will look like if you were to take many, many, many samples from the same population. This seems a little arbitrary, because of course, when would you ever want to take 100,000 samples and know how they're distributed? But there is a purpose to it, and it's the underpinning for what everything that we do in Statistics 1B. Not everything, almost everything we do in Statistics 1B. So that's why we're talking about this so much. Not much practical use, very important theoretically. Now, one of the biggest goals that we have is that when we have a sample means distribution like this, that we want to calculate probabilities. Now, when we actually have this distribution, it's fairly straightforward. To put it a little bit, to start off with a more basic example, back in the old days, very old days, in the 90s, we didn't all have computers or smartphones or tablets, but it was very common for people to have just one computer, which would be the family computer, and so everyone would share just one computer, and everyone would do their business on the computer. So everyone had to share it, which also meant that you could record how many times anyone was active on that particular computer. Now, let's say the computer was on 80 hours a week, and on average, my brother used it 10 hours, sister used it 20 hours, father used it 40 hours, mother 8 hours, grandpa 2 hours, and grandma 0 hours per week. Just as an example. Given that the computer is on, you can then calculate the probability that a particular person is there. For example, of the 80 hours the computer was in use, my father used it for 40 hours, which is 40 divided by 80, which would be exactly half. So the chance that, given that the computer is used, that it is my father using it would be 50%. Similarly, my sister used it for 20 hours out of 80. In that case, 20 divided by 80, 0.25, 25% chance. Mother did 8 out of 80 hours, 8 divided by 80, 0.1, 10% chance. And such, you can calculate the percentage for everyone. Of course, grandma 0% because she never used it, 0% chance. So in that sense, we can look at the total of 80, and then we can take whatever we're interested in, and then we can divide it by the total number of hours. You could even do it by generation and say, oh, what's the chance one of my parents was using it? Well, both father and mother is included in parents, obviously. In total, they used it for 48 hours. So then 48 divided by 80 would be 0.6, and that's 60%. So probability is always a measure of x. I'll write this down. I'll actually write this down too. It's always a measure of x divided by n. X is the amount of hours that it fits whatever you're interested in. Like, for example, parents or father or mother or siblings or brother or whatever, divided by n as the total amount of computer hours. So it's always this particular ratio. That's always what a probability is, and also proportion. Now this logic even applies here. Now, of course, it's a bit hard to read, but theoretically speaking, if, for example, you're interested in the chance of finding, for example, an average that's lower than 95, you can literally sum up all of these bars. I'm assuming you can see that. Yes, you can. Okay, good. You can sum up all of these bars. Those will be the x's because they meet the criterion of lower than 95. You can sum up all of these. And you can divide that by the n, the total number of samples, which in this case is 100,000. And that works. So probability is really just about counting the amount of x's that fit whatever you're interested in, divided by the total number of whatever it is you measured. So in this case, let's say maybe there are 3,000 samples in this range. Purely a guess, by the way, I have no idea. 3,000 samples in this range, then it would be 3,000 divided by 100,000, which is 0.03. So 3% of samples scoring below 95. That is all probability calculations are. That's one big problem. Of course there is. In practice, and this is where we move on from statistics 1a to statistics 1b a little bit. This is the crossover point. The big problem here, core problem, is that we don't actually know this. Now, of course, like if there are theoretical exceptions. For example, one case in which you do know the entire population is if you would check the last 20 years of statistics 1a grades, for example. You have all of them, like the university has all of them. They can technically look up, I'm pretty sure they have it in a database somewhere. They can technically look up all the grades from the last 20 years and then just use that as a population and then say, well, what is the probability that the average of just like 10 random people in this has a 6.5 or higher? Or what is the probability that these what is probably that if I pick 20 random people from the last 20 years, what is then the probability that they're going to have between a 5 and a 6 on average? In those situations, you can actually calculate this sample mean thingy because you have the entire population available to you. But as you can imagine, in most cases in psychology, you do not have access to the whole population that you're trying to generalize towards. It's very uncommon. So not knowing the population means we also don't know exactly what this distribution is. And yet we still are interested in calculating probabilities. How does that work? That's what we're about to find out. So what's important is we need to know both the general shape of a distribution and we have to assume specific characteristics of the distribution. So we don't know what this shape is, but we still want to know it. We don't know what this exact distribution is because we don't have a population, but we still really, really would like to know what it is. And so we need to know if it's normal or if it's uniform, or if it's logarithmic, or if it's even a different kind of distribution, exponential, whatever. And we need to know once, or binomial for that matter, one we actually learned. And on top of that, we need to also know the specific characteristic. For example, if it's a normal distribution, well, okay, you have the general shape, that's good, but you also need to know the mean of that distribution and the standard deviation of that distribution to exactly define it. Just like for the binomial distribution, you needed to know the sample size and the probability of success to define the exact binomial distribution that you could find. So it's not enough to not know, even know the shape. You need to know the exact characteristics of it as well to properly define it. And that's really hard when you don't have access to the population whatsoever. But that's what we're learning. So for sample means, the distribution is usually normal. And that's because of the central limit theorem. And this is also something that's was introduced in statistics 1a, but still very relevant, which is this is a description of the phenomenon that as the sample size increases, the distribution of the sample means becomes more like a normal distribution, regardless of what the starting distribution looked like. Now, this is more of a scale thing, so it's more like every time that the sample size gets larger for each sample, the distribution of the sample means becomes more normal. So it's like 6 is a little bit more normal than 5, 10 is a little bit more normal than 5, is a lot more normal than 5, 15 is more normal than 10, 20 is more normal than 15, and 1,000 is even more normal. It's a scale that the larger the sample gets, the more normal it becomes. The reason you might learn cutoffs, it's not that it doesn't work below it and it does work over it. It's more along the lines of to say, if you have a sample size of, let's say, 15, then in most cases, unless there's something really not normal going on, you'll end up already with a normal distribution for your sample means. If you have another cutoff that you might see often is 40, and again, for 40, that's large enough that, and you can kind of already see it here with 30, that regardless of how it started, they all kind of look like normal distributions with 30 already. And 40, definitely, like, even if it's basically the most wrong distribution you can think of, by the time you have a sample size of 40 and you make a distribution of the sample means, it's all virtually like a normal distribution. So the phenomenon applies at every level, like it's a scale. It just becomes more and more and more normal once your sample size increases. So every extra person counts in that regard. But you might see cutoffs as like, okay, if you hit that level, then you're basically fine. Like you're always going to be fine. And with 15, you're going to be mostly fine. If it's below that, it doesn't mean it's poor, but you just have to make sure that the original distribution, or that the scores are actually roughly non-distributed, so that it's, otherwise you get something that looks a bit silly, like this is not a normal distribution. This is closest, but it's still a bit skewed, and this also looks a bit weird. So as you can see with 5, that's very small. In that case, your distribution might not actually look like a normal distribution, and it would be wrong to treat it as such, because then the distribution you assume is not the distribution that you actually have. And if there's a mismatch there, nothing you calculate can ever be correct. So based on that knowledge, in practice, you probably have a sample size of, well, bigger than 5. Most research has samples bigger than that. Bigger than 15, also bigger than 40. So for that reason, in practice, having a normal distribution is extremely, extremely common and likely, which is also why the course focuses on it. It doesn't mean it's better. It's just that this situation applies in practice so many times, 90% at least, I would say, that it's a good place to start, because if you know how to handle this, then you can do the method that is most appropriate for the situation you're in most cases, which is good. But that doesn't mean that it's the only type. Like if you don't have a normal distribution, there are other tests that have other distributions in mind that you might be able to use. That's in the larger field of statistics again. So don't think of it if it's good or bad, but for the methods we're focusing on for now, we're going to focus on the normal distribution because of central limit theorem. That's why it's so prominent in what we do. Now, we also, when we have a normal distribution, we also need the mean and the standard deviation. If we want to estimate that. For the population mean, we don't know what the actual population mean is, but we can make a realistic or a relevant estimate. Now, how that works, we'll see later when it's relevant. And with the standard deviation, at least in the beginning, we do assume that we know that. Now that's of course a bit of an arbitrary situation, because it would be weird not to know the mean, but to know the standard deviation of the population. It's quite uncommon, I would say. But we use this as our current example because it's the most, it leads to the most straightforward calculation. So this way you don't get distracted by anything. You can just focus on the concepts first and make the calculation as small as possible. And then you can add the rest of your concerns later. So this is it's not impossible for this to happen. There are situations in which this can all work out. It's rare though. But it is very convenient mathematically, which is why we start with it. So it doesn't, so you don't get introduced to too many issues all at once. For the standard deviation, and note here, this line is extremely important. The standard deviation of the sample means, of the sampling distribution, is the standard deviation of the population, sigma x, divided by the square root of n, where n is the sample size. For any particular sample, like how big was that sample, or are all those samples? And this formula is probably familiar, but the most important thing to remember is there's a big difference between this x and that x. This is for the sample means, the sampling distribution, and this is for the population distribution, for the how individuals in the population are spread. And so that leads us to make various assumptions in what we just did. First of all, just to put it officially, the distribution of the scores is normal. We assume that here. Now, of course, there's the central limit theorem. This is usually met, but it's something worth keeping in mind, especially when you have small samples. The standard deviation of the population has to be known, because, of course, otherwise you cannot calculate it. So this has to be known, because, of course, if it's not known, then you can't calculate it. And then, of course, well, what do you do then? We'll learn about that later. And in this case, we also, and this is not just in this case, but this is taking a little bit of a step back, but always important to remember. When you take a sample of the population, and this includes everything you learned from statistics 1b to the end of time. It's a bit dramatic, but statistics 1b, statistics 2, and statistics 3, and even in the master courses, if you're going to take those here, every single time you do any sort of generalization from a sample to the population, whatever form it takes, it has to be that the sample is representative of the population and that it is unbiased. Because if you're taking biased samples, then by definition, everything else falls apart. Because of course, if you have a biased sample, like you can't calculate the probability to find an IQ 110 or higher from the general population if you handpick the people in it. That changes the probability completely. If you just handpick the people you know are the smart, or at least you assume are the smartest, then you're probably going to get an outcome that reflects that, with a lot of people who score really high. But it isn't as if the probability you calculate is as if you took a random sample from it. truly random sample from the entire population. That's what is assumed. So if you don't, and you just handpick people, that's of course an extreme variant of it. But if you take a biased sample, the probability for that is both meaningless because you literally pick them, but that it makes everything else fall apart. So the assumption here is always that it's a random sample, and that's also an assumption that will be why it's running through everything you'll ever learn about this topic. So quite important, but so it won't be repeated every time. Like, oh, by the way, it has to be unbiased. Or this won't make sense. So this is just something that's going to be true all the way into the future. These two, not always. Although this is very common, or explained for reason, but not literally all the time. But this one is fundamental to everything we learn. Everything. Otherwise, none of our results really do anything. So, even without knowing, even without having computed any of the samples, this is the magical part, I think, of it. I think here we had to take, originally we had to take 100,000 samples to find the distribution of how the scores were actually, how they ended up, essentially. And I registered all of them, and I just, reported what exactly the sample means were and how they were distributed. Okay, good. So this is just exactly, if you actually did take 100,000 samples and you recorded all the sample means, this is what you'd end up with. Now you can see that this is a normal distribution and that it has a mean of 100 roughly, and that the standard deviation is following this formula, this one. But now, because of these assumptions that we've made, okay, it's probably going to be more normal. For our convenience, we're going to assume it's a mean of 100. We do know our standard deviation. And we're going to assume unbiased samples from it. Okay, perfect. Then and the sample size also is 80. Okay, perfect. Then it should look like this. And that's without even taking the samples. Now, I'm comparing it because here we actually did take the samples, and so we know this is true. Because, in this case, it's over the same date that we took all the samples. We saw that this was indeed the case. But now, just based on these assumptions, we can recreate that without even needing to take the samples. And this is the magic that we rely on, essentially. So the core of statistics 1B is inferential statistics. Just to make this a proper overview. Inferential statistics is all about taking a sample and trying to generalize it to the population. What you see here is how we can do that. So based on the information that we do have from our sample, we assume this in the population, like that the distribution of all sample means is like this, so that we can test how our sample fits within this distribution and then draw conclusions based on that. That is the key. We make educated guesses of what the population looks like based on what we recorded in the sample, what we collected. And then working with those assumptions, we can calculate probabilities that might help us detect whether a pattern is generalizable to the population, or to estimate what the population value might be. Without actually knowing the population. And that's a very useful trick. So what we really want to do, and this I think is around the time where Statistics 1A ended, what we really want to do is be able to calculate the size of specific areas. Of course, we have this beautiful distribution. Okay, that's cool. But for example, what is the chance that I'm going to find 97 or lower? Well, what's convenient about these curves of these distribution that we made, and this is a really sneaky thing that was technically mentioned in 1a at one point, but whenever we make a graph like this, which is called a density curve, the total area under the graph is exactly 1. So what we did, and what we can do, is that we can calculate the size of the area that we're interested in. So for example, if we're interested in 96.7 or lower, we can just take this part of the graph, calculate the area for it using this formula, among others. And using that, we can actually literally calculate the size of the area to find the proportion of scores within that area, and then, because it's the same, and then also by extension, the probability for a random value of the distribution to be within the area, which is what we're interested in. So now, of course, a bit of a problem is, I don't know if you've had geometry. It's already, you probably learned how, if you had geometry, you probably learned how to calculate the area size of like a triangle or a square or a pentagon, perhaps. But what you probably didn't learn was how to calculate the area size when the curve was bent like that, where it wasn't just a straight line, but a part of curves. Because it's, you'll probably also have the area of a circle, but this isn't even a circle. It's just part of like a curved line. And well, you do have the formula for the exact curvature, but as you can see, that's also quite complicated. So calculating the area, as you can imagine, mathematically is not a fun task mathematically. There's quite a lot of numbers you have to fill in just to get the exact area out of it. So that would be very frustrating. Fortunately, there's a little help for us in the form of this table. So now also computers. In practice, you just use a computer. You wouldn't bother using tables because it's just it's not as quick. Computers are easier, give you more information. But for our exam, we need tables, so we're going to learn how to work with tables. Now, so what the table is basically done is that for, in this case, table A, the entire table A, it ranges from minus 3.49 to plus 3.49, which essentially means there are 700 different points in this graph, in this normal distribution, 700 different points. And for each of those 700 points, ranging from minus 3.5 to plus 3.5 to keep it simple, it gives you the probability to find that value or lower. I'm mirrored, I think, so that way. Yes. So the table A always gives you the probability to find a particular value or lower. That way, yes. So for example here, if the z-score is 0.00, just exactly the halfway point, then exactly 50% distribution is below it. If you have a z-value of 0.01, then 50.4% distribution is below it. 0.02, then 50.8% distribution is below it. Now, you can keep going, and every time you get exactly what percentage of the distribution, what proportion of distribution is below it. It's literally also the area size. So it gives you the area size of this blue. Is this blue? Well, yeah, definitely the blue. I'm gonna go with blue greenish. It just gives you the area size, which is also the proportion of scores below the value and the probability that any outcome is within that range. So that is the fact that it's the value or lower. This isn't like a uniform thing. The table could have been made in many different ways. They could have also listed the right-sided probability. They could have, but they didn't. They listed the left-sided probability. This is also why I think it's important to work with this table specifically, because another table from another source might be structured differently, and it's not worse. But if you're accustoming yourself to a different table, and then you get this one on the exam, you might treat this table as if it was a different table and get wrong results. So stick to this one. Get comfortable with it so that you can find the corresponding probability given any z value. And here's just an example. Say that you're interested in the, for example, if you found z is 1.28, then you can look it up here and see that 89.97%, so basically 90% of the distribution can be found below it. Now, just as a little test, find z values for the middle 20%. So for this, let me clear this quickly. Okay. So for the red one, we could see that 0.4, no, I should say 40% of the distribution is below it. And for the pink one, it's 60%. And this is what matters, because again, table A always gives us the probability of defining that particular z value or lower. So the only question we ask ourselves is, how much can we find below it? Well, for the red arrow, we see here, apparently there's 40% below it. Okay, cool. So we want to, whatever z value is, it has 40% below it. For the pink one here, it has this 40% below it, but also has the entire range of the 20% below it. Like this entire area is below it, 40 and 20%. So in total, that's 60% distribution below it. So if we were to look up table A, we would look up 0.4 and 0.6. 0.4, 0.4. That's not perfect. That's not an exact 0.4, but the closest one is this out of all of them. And that would be minus 0.25. Okay, so that means the z value is minus 0.25, because for that particular z value we can find 40% of the distribution below it. Now we do the same thing for 60%, and well, again, this is the closest, and unsurprisingly, because normal distributions are symmetric, it's 0.25. That is closest to it. So now we have found the standardized scores, and we know that if for z is minus 0.25, we find 40% below it. For z is plus 0.25, we find 60% below it, which is exactly what we wanted here. This is exactly what we were aiming for here. So now the only question left here, and this is also immediately a good test of, if you remember how to unstandardize, how to transform a z value back to an actual score, given that we know the population mean of 100 and the standard deviation of sample means, which is 2.12, which we saw prior. The formula for that is that the score, the x, is equal, oh wait, I'll take a different color, just, there we go, x, and I'm gonna start with the red one first. It is the population mean plus, and then we take the z value, which is 0.25, times, and then we multiply it with the standard deviation of, and then specifically again, note, this is the standard deviation of the sample means. So this is not the population standard deviation, it has an x bar. So this has already, so to speak, this has already been divided by the square root of n. This is It's this one. We already have this one specifically. So we don't need to we don't have to divide it by square root of n of anything. And that gives us 99.47. Does that fit here? Probably not. I'll write it here. There we go. This is a 9. Similarly, we can, there we go, I have some more space. Similarly, we can do it for the pink one. And again, it would be the same formula, so it's still 100 plus 0.25 times 2.12. And this time the outcome will be 100.53. It fits, barely. Can't really write. 100.53. So with that, we know that the middle 20% of sample means will be between 99.47 and 100.53. Very cool. Finally, this will end the part on statistics 1a. We keep talking about that it has to be normal. Just wanted to give a small demonstration of what happens when it's not normal. Here we have a population distribution, and it's a uniform one. Well, not perfectly, but the intention was that you have scores from 0 to 100, and we have 10,000 people, and they're completely fairly distributed among all the 100 points. So essentially, you get 1,000 people who score between 0 and 10%, or 0 and 10. You get 1,000 people who score between 10 and 20. You get 1,000 people who score between 20 and 30. 1,000 people who score between 30 and 40, etc. So it's always 1,000 people per 10 points, essentially. It's all completely fairly distributed. So essentially, the probability to get any score in the entire range between 0 and 100 it's always the same. So the chance to get between 40 and 50 is 10%, and the chance to score between 0 and 10 is also 10%. 10 and 20, 10%. 20 and 30, 10%. 90 and 100, 10%. It's always the same. If you, however, assume a normal distribution, you would not assume this. So for example, here we can see that there are approximately 1,000 out of 10,000 people. Let's take this one. Approximately 1,000 of the 10,000 people score between 90 and 100. So what is the probability that a random person from this entire data is between 90 and 100? Then the real probability is 10%. Because this is the population, we can see that. But if you take the normal distribution, you would instead calculate this area, but like basically below this black line down here and then up again here. And you will get something like 3%, because that's the size of this area below this line. The line doesn't match the actual data whatsoever. It overestimates how many people will be in the middle, because for this distribution, it's all 10% all the time. It assumes more people are here. It assumes less people are here in the edges. And then again, it doesn't even stop at 0. We can see there's no person whatsoever. There's no chance at all to find anyone who scores higher than 100 or lower than 0. But based on the normal distribution, that would still be 1 or 2%, which is again wrong. So really what it's just trying to demonstrate is that the methods that we're learning are designed to work for normal distributions. The table works for normal distributions. Everything we do is for normal distributions. It's not terrible if it's not a normal distribution. There are still ways to calculate probabilities. We just did. We can still calculate probabilities based on this. There's no problem. There's nothing stopping us from doing it accurately. It's just that using a normal distribution doesn't fit. And that was also the problem with the binomial lecture from Statistics 1a, is that the reason you needed a sufficiently large sample to be able to approximate it normally is that otherwise the distribution wasn't normal. So you just pretend it's normal even though the distribution looks nothing like it. And that leads to inaccurate numbers or outcomes, of course. So if you assume a distribution and it doesn't follow a distribution whatsoever, whatever you get is going to be a bad outcome. So that is just the problem with it. It's just, if it's not normal, then, well, you can use other methods. You should use a method that actually assumes the right distribution. There's nothing, like, it's not catastrophic. Like, you didn't fail as a researcher, but don't use methods that assume normality. Good. Now, that was the setup for Statistics 1a. I thought it was really important to highlight those pieces again, because as we'll soon see, we'll be using those a lot going forward with pretty much all the different lectures. But yeah, pretty much all the different lectures. Except maybe the last one. So if you need to take a break, this is the perfect time to do it. But if you're still good to go, then I'm going to continue. Fortunately, you can pause videos. I love this setup. See, it's so much better when people can just take breaks whenever they feel like, and then continue when they can. No matter the attention span, everyone can use them. Good. So now we've arrived at Statistics 1b. And Statistics 1b, as I highlighted before, is all about inferential statistics. And the fundamental question we ask ourselves is, we have a sample and we want to generalize it to the population somehow. Now, the fundamental issue is that we don't actually know anything about the population or how our particular sample fits into the population. Like, even in a perfectly random sample, you can be very lucky or unlucky, I guess, and just happen to get a sample of like all the people who score the highest. They just all happen to find a way in your sample. It can happen. Or the other end, that people just all score very low. There's no guarantee that your sample is representative, really, because you just don't know. If you use proper methods to sample as randomly as you possibly can, that's the best job you can do, and no one would expect you to do more than that. It's just like, that's the best you can do. But in reality, you really don't know for sure. And that's the fundamental issue that we run into. And this is also why there are so many different philosophies around how to approach it. As especially with lecture 11, you get introduced to a different philosophy. There are two mainstream ones. You can kind of see the frequentist one and the Bayesian one. But these exist because there is not one answer that is objectively correct. There is there's this part where we have to estimate it as best we can, reflecting the situation that we're in, and then trying to find an approximation that best suits our needs, that does the best job in the situation where we only have the data and we're trying to say something about the population. But there is no certainty in any of this. So that's why there are different schools of thought on this. And this might be a bit jarring because for most people, when they do anything mathy, and considering there are tons of numbers already above my head, and also throughout the course, like, it feels very mathy and like you're calculating something exactly. But at the same time, the very fundamental core of inferential statistics specifically is that we can never really be sure about how it fits in. And so what we're calculating is meant to help us make educated guesses. It isn't, you're not calculating towards a final definitive answer that the whole world will agree on and we know 400% sure is correct. But rather, we're calculating things that help us estimate and make an educated guess about the trends that we observe. Because it, like, if you're being very strict, we can never be sure. But on the other hand, it's also unfair to say that you can't say anything whatsoever. Using IQ again as an example, if you, like, assuming that indeed for the whole population the average is 100, if you consistently have a particular group scoring 120 time and time and time again, then it is more reasonable to assume that they on average have a higher IQ than the average, because this group seems to consistently score above it, above it, above it, above it, above it. Now, and of course, technically speaking, it could all just be luck. But the chance that maybe they just fundamentally score higher becomes more and more salient. It becomes it becomes the option that makes more sense. If you have a lot of evidence towards that, you're going to assume that. And similarly, if you have people claiming like, oh, this group will have super high IQ, but then you take a sample and you find 101, 99, 102, 100.3, something that's very close to the average, you wouldn't immediately be convinced that that group is indeed a group that scores higher than the average, because, well, data doesn't really support that notion. It's like, well, yeah, 101 is higher than 100, but you're not immediately as convinced as you would be when you find 120 on average. But of course, as a researcher, it's if you have these very clear-cut examples where if you have a huge difference, like between IQ of 100 and 120, that's such a big difference. It's like, well, probably the 120 is higher. Or if you have, like, for example, 100.1, it's like just like basically no difference, that you would say, well, probably not that different. Those examples, you don't need any help from statistics really to confirm that it is indeed different, because the patterns speak for themselves quite loudly. But what's difficult is that in most cases you don't get something so clear cut. You get a lot of noise, you get a lot of different variants in your data, a lot of data points that go all the way, and you really want to hone in on what's specifically important to you. And so these methods that we learn, they help us make these educated guesses by focusing on the information that's relevant to us and converting that into estimates and numbers that, once we learn how to interpret those estimates and numbers, can help us make better educated guesses. And the point isn't to be right in every individual case, but the point is to be more right than wrong in the long run. And even with Bayesian statistics, it doesn't, as you'll see later, it doesn't claim to be right in every case. It just tries to make the best estimate. And that's what it really is. These tools help you make the best possible estimate. So it's not useless, but don't expect the outcomes to be hard truths either. So it's somewhere in the middle between that. We don't know the truth, but at least we can make good guesses. And so throughout the course, we learn how to do that, where the first 4 lectures focus really on just the fundamentals of how frequentists work: confidence intervals, significance tests, effect sizes, and power as additions to significance testing. Then lecture 5 through 7, we expand on that. Like, we continue with means, but we find different situations, different types of data. And finally, we apply it to proportions and also frequencies, like, well, how do you calculate with them? And so that's most of the course. But the core of it is that we learn about confidence intervals and significance tests in the first 2 lectures. And then we spend the rest of the time essentially expanding on those and finding extra, and then doing significance tests and confidence intervals for different types of data, and how to recognize those data, and then how the formula changes. But in the end, we're still doing a significance test and a confidence interval. And finally, we get a little lecture on Bayesian statistics, which is a fundamentally different philosophy, which we'll explore there. But this is also the entire course. So especially the first 2 lectures introduce the 2 big topics for this course, which we will expand on for the 10 lectures out of 11. And then we have 1 lecture doing something different. So that's also the entire course. So now for the rest of this lecture, we'll actually focus on confidence intervals and what it is. So to introduce confidence intervals, we're going to stick to the most straightforward type of data that allows to calculate an actual confidence interval with as few mathematical components as possible. So that's why we start with what we start. But the idea in general is always the same. A confidence interval is that you took a sample from a population, and of course, based on those results from our sample, we want to estimate a parameter. So for example, you have a sample, we found a sample mean. Okay, cool. But based on that, I want to say something about the population at large. For example, again with IQ, or take something else, extraversion. The general population, let's say, scores 50 on average. We found a group we have a sample of a particular group of people, and they have 60. Okay, so it's higher. So what can we expect from the entire population of this group of people? Like, let's say it's a group of customer service reps, for example. I can imagine they probably have an easier time talking to a bunch of people. Maybe they score 60. Well, you take a sample of those people, you find 60. Okay, so what do these people score in the population? What can we assume? Now, of course, we don't know for sure because we didn't measure the entire population, but if we have a sample, a random sample, and we find 60, then it is reasonable to assume that the population is probably going to be somewhere close to 60, maybe 61, maybe 59, but probably not 30, for example. That's very far away from that sample. It will be very unlikely to find a sample mean of 60 if the population mean really was 30, because that's so far away from it. So, but of course, we can just guess, but we would like to have some numbers to help us make this estimation, and that's what the confidence interval is for. So we do this based on an assumed distribution. There it is again. Assumed distribution of the relevant statistic. So for example, like we saw here, the assumed distribution of the sample means, like here. So we use this to our advantage to estimate where the population mean could be. And we use a procedure that leads to an interval that includes the parameter most of the time, because we can never be sure. And that goes back to what I was just talking about. It's very important to remember that you cannot be entirely sure. The samples, at least you assume, are randomly selected from the population. Sometimes you get a very high or low scoring group of people, and therefore we don't know how our sample compares to the population. So this highlights yet again why it is that we're never going to be 100% sure. But as I previously mentioned, the point is to make educated guesses. We can pick different levels of confidence, and what the confidence level reflects is how much of that assumed distribution is included within the confidence level. So for example, if the default is 95%, if you take a 95% confidence interval, you take the middle 95% of this distribution. If you take a 80% confidence interval, you take the middle 80% of distribution. If you take 99%, you take the middle 99% of this distribution. So the good thing about going high is that more confidence means you include a bigger part of the distribution, which is good. And because it basically means you include more possible, you include a higher proportion of the values that you think it might be. which is good because it's good when you try to estimate a population mean and the population mean is actually in the interval. Of course, what's the point of making an estimate and then not having it in there? So that's why also the default is 95%, which might feel a little high. Why 95? Because that's pretty high up there. But that's because you generally want to be quite sure that what you're trying to estimate is actually in there. Because, for example, if you have a 20% confidence interval, to take something really low, then only in 20% of the samples will the parameter be included. That's not enough. That basically means 1 in 5. Then you do 5 samples, and only in one of them is the real parameter included. That's quite low on average, 105. But so with 95%, it's high enough that you can feel fairly relaxed and that's included without pushing it so far that it becomes meaningless. So it now probably makes sense why I wouldn't take a 0% confidence interval, because of course 0% then, well, there's no interval really. Then you would have no chance of including your parameter. But why not 100, you might ask? Because of course it's great, if it's good to have a more confidence, then why not take 100%? It's because the normal distribution is technically infinite. It can range all the way from minus infinity to positive infinity. And so the only way to be 100% sure that your value is in there is to have an interval that ranges from minus infinity to positive infinity. Now, of course, it's true that the real population mean is somewhere between infinities, but it doesn't really help us. And this brings us to the other consideration, where you want the confidence interval to be narrow. The problem with getting more confidence is that you need to include more and more and more and more of the distribution to meet those confidence levels. But then you make your confidence intervals so wide that it doesn't tell you that much. If you say, well, you want to say something like, well, I estimate the extroversion to be between 58 and 62. Because then, then it's a pretty narrow range and the parameter is probably somewhere in there, which is pretty useful. If you say, well, it's somewhere between 20 and 100, then it's like, well, yeah, you're probably right. But the whole scale is from 0 to 100. So saying these people are between 20 and 100, it's like, yeah, I mean, I guess you narrowed it down slightly, but there's still leaves a lot of room for where exactly it is. So you want it to be both narrow and confident, and those two tend to run up against each other. So that's why 95% usually thought of as a balance, but this is also why it's not set in stone. There are situations where you absolutely want the parameter to be in there and you can go higher. 99%, for example, is a common alternative. And there are also situations where the narrow, like you want something narrow enough and you need 95% doesn't give you anything narrow at all. So then you can go to, for example, 90% to just make it a little less confident, which isn't ideal, but it does at least give you an interval that's narrow enough that you can work with it. Like you sacrifice a little bit of confidence to have an interval that's a lot narrower. In practice, you can decide, like in the world outside. Although most people would say just stick to 95%, like that's most of the research. But on the exam, for that reason, they'll always tell you. If they don't tell you, you can safely assume 95%, because that's basically the default. But in almost every case, I can imagine they will always tell you what exactly the confidence level was that they're asking of you. So definitely pay close attention to that so you know what it is, because it isn't always 95%. It doesn't have to be. It's very likely you get at least something that's not 95%, but it will always be in the question. I will always mention it. So the definition is, and this is important to keep separate, in the long run, 95% of 95% confidence intervals will include the true parameter. And so it's wrong to say and this is important, there is a 95% chance that the parameter is included in a confidence interval. Now, on the surface, the reason I bring this up is that on the surface, these two look very similar. But it's when it comes to statistics and probability, it's very important to know exactly what the probability is about and what exactly you're calculating. And being imprecise with wording can be judged quite harshly, especially on the exam. So the difference here is that the randomness is in the sample. So if we take 1 million samples, then in 95% of samples, in the long run, the 95% constant interval will include the true parameter. The reason you can't say there's a 95% chance that the parameter is included is because it implies that if you could take more confidence intervals, then it sometimes will be included and sometimes will not be included. But if you calculate a confidence interval over the same sample 100 times, you're not going to get different results. So the difference is this: if you have a class of 100 people, and I give, let's say I have a class of 100 people, and I give all of you exactly the same data set, and then ask you to calculate a confidence interval, then either all of you, assuming everyone calculated it correctly, either all of you will include the parameter or all of you will not include the parameter, because it all depends on the sample that I have given you. If the sample is close enough to the if the sample mean is close enough to the population mean, it is included. If the sample mean happens to be one of those extreme samples where we find a lot of people who don't score like the rest of the population, then we will not include the true parameter. But it's not, it's either all of you will get it included or all of you will not include it. However, if I have a class of 100 people and I give all 100 of you a different data set, so that I have 100 samples and each person gets a different sample, and then I ask all of you to calculate a confidence interval, assuming that it's done correctly, then on average, 95 of you will find that the parameter is included, and 5 of you will find that it's not included on average. Of course, sometimes 96, sometimes 94 because randomness, but that's the core difference. So it won't be 100 to 0, all the same results for the same data set. You will now get, because you have 100 different samples, you will get 95 people who indeed find the parameter within it and 5 who don't, because it's all about the samples. So you can't say it's 95% chance that it's included, because it's not as if we all calculate the same confidence interval of the same sample, it's not that we all have a 95% chance. That calculation is just a strict set of procedures, and the randomness has already happened, which is when the sample was collected. So be careful with the wording, because this would imply that if we all calculated the same confidence interval, that sometimes we get different results. But that's not the case. The randomness is in the sample. So now that we have a better idea of the logic behind it, the logic, by the way, this always applies. So even when you go into the future, these ideas and the way confidence works and the definition, how to interpret it, these things apply forever. This is just fundamental to confidence intervals. Now we look at how the calculation works, and we start with the more general idea, and then we apply it to the case that we've been working with so far. So we use our sample to estimate distribution of sample means, to make an educated guess of what this looks like. We do that based on the sample and certain assumptions that we make. And for now, I'm going to stick to 95% because it's the default. So there's a 95% chance that a randomly chosen sample mean belongs to the middle 95% of all sample means close to the population mean. So then we take the distance between the population mean and the lower and upper bound. That includes the middle 95% of sample means. So essentially, actually, let me just draw that. Where was I? There. There we go. Yeah. So we created this distribution based on our sample. We assume that this is the distribution of the sampling from the sample means. We then take, okay, we want the middle 95% of the scores. Let's say that's this part. And well, that's the middle. That's the population mean. And now for convenience, let's say that 90. Actually, I'll take different numbers. Let's say the mean is 10, and that we can find that we've determined that 95% of the scores are between 5 and 15. For example, let's see, can I just, yeah, let's look at that. Okay, you get the idea. Yeah, good enough. So the exact calculation for this we'll save for later, but let's say that based on our sample, we've estimated distribution. We did that, the red line. Then there's a 95% chance a randomly chosen sample mean belongs to the middle 95% of all sample means close to the population mean. So we have this blue area for that. And then what we're interested in is that we take the distance between the population mean and the lower and upper bound. And that distance is 5, because the distance from 10 to 5, well, the distance between 5 and 10 is 5. And because normal distributions are symmetric, it's 5 both ways. So what we do here is that when we reverse, so what we do know here is that for 95% of sample means, the distance between whatever the sample mean is, and the actual population mean of 10 is 5 or less. For example, if someone scores exactly 5, they get randomly Furch, the distance is 5. If someone scored, for example, 8, the difference between 8 and 10 is 2, which is also less than 5. If someone scored here, that's 13. Oh, that's also a very poorly visible color, I just realized. So 5, that difference is 5. For 8, the difference is 2. For 13, difference is 3, but it's still less than 5. In fact, the only time you find a distance greater than 5 is if you're like one of the most extreme samples. For example, here, if you find 17, then the difference is 7, which is greater than 5. But that's a pretty extreme sample. So what we see is that for 95% of samples, the distance between the sample mean and the population mean is indeed less than 5. So, reversing this, if you have a sample mean of 5 and you create an interval of 5 around it, then it will indeed include the true parameter, which is 10. Also for the 8, like if you found 8 and you include the 5, if you have that interval of 5, then you indeed found 10. If you take the 13 and you make an interval around it, well, that goes from 8 to 18, the 10 is still in there. Only for 17, then the interval will be from 12 to 22. The true parameter is in there because 17 is a very exceptional sample. So what's happening here is, for 95%, we know that for 95% of the sample means, if you take 100,000 samples, then for 95% of sample means, the distance between it and the population mean is 5 or less. So if we were to create a confidence interval with range 5 around all the sample means, all 100,000 of them, then in 95% of cases, the true population mean of 10 will be included, and only in 5%, like that 17, for example, if you make an interval of 5 around that, it will not be included. So that's the logic that's being applied here. First, you look at in how close are 95% of the sample means. Well, in this case, distance up to 5. They're up to 5 points away from the population mean. Okay, so if I make that same interval around each sample mean, then in the long run, 95% of those intervals will include the population mean, unless you have one of those extraordinary samples, extreme samples like the 17, where the distance is too great for it to be included. In this case, it would go from 12 to 22. And of course, that doesn't include the 10 that we saw before. So that's one of the 5% where it doesn't include it. So that's the logic behind it. You look at how the sample means are compared to the population mean, but then we use that logic to our advantage by swapping it around and saying that in 95% of the cases, the population mean is this close or closer to the sample mean. So how we end up calculating it, the confidence interval, is taking the statistic and then taking plus minus the so-called margin of error. This is always the case. Two things to note here. For one, there are many intervals, even different intervals in the core statistics 1b. Not all intervals are confidence intervals. A confidence interval specifically is an interval where you have a statistic and you're trying to estimate the corresponding parameter. You can calculate different intervals and they can be perfectly valid and fine, but they are not called confidence intervals. So here we're specifically talking about the confidence interval. Now, so and also I'm highlighting this because it's important not to conflate that with, I would say, other types of intervals and pretend that they're all confidence intervals, because other intervals will have different types of ways to calculate it, you may be calculating something different altogether. Second, the statistics plus minus margin of error is always the case, and it also highlights that any confidence interval is exactly 2 margins of error. So in this case, we have the margin of error for the example above me is 5, because the margin of error is the distance between the statistic and the lower and upper bound, essentially. So it's the distance between 17 and 12, or 17 and 22, both of which are 5. So the margin of error here is 5, and the total length of the interval is 5 plus 5 is 10. It's always exactly 2 margins of error, because you have one margin of error one way and one margin of error the other way. So total is 2. Now, of course, then the question is, how do we calculate the margin of error? Well, that's where the formula comes in this case, which is that we take a test statistic and we multiply it with the standard error. That's the generic formula for it. Again, that's the one that always applies. And you'll see that a lot later as well, where it's always going to be a test statistic times the standard error. Now, what does that mean? That's what we're finally here for. The example we use is that we have a single mean, and that we just took a sample of scores, and we want, let's say again for extraversion, and we want to know that we found a sample mean of 60, and we want to estimate what the population mean could be based on that. We do know the population standard deviation, but we have no idea about the mean. Slightly arbitrary example, but very mathematically convenient. So to calculate it, you take the sample mean plus minus the margin of error to calculate it. Okay, cool. And the margin of error can be found this way. So the X would be the sampling, the statistic that you're interested in. That's the statistic that we're interested in. The Z star, that's the test statistic. And a test statistic, at least for confidence intervals, will be either a Z or later a T score. It is essentially the test statistics are always a connection between your actual data and probabilities, because they're very known, well-specified distributions, so they can be used as conversion tools essentially. And finally, times the standard error. The standard error is the standard deviation of a statistic. So again, also important to know, the standard error, what the definition of that is that it's the standard deviation of a particular statistic. In this case, the statistic is a sample mean. So we want the standard error of, specifically the standard deviation of the sample means. And we learned previously that we can find that by taking the standard deviation of the population and dividing it by the square root of n. That gives us standard deviation of the sample means. Now, what's important to remember with this is that if you have a different statistic, and later on you will learn about different statistics, especially from lecture 5 going forward, you will learn about different statistics, and that also changes the standard error, because every single statistic has its own standard error, because it's always the standard deviation of the statistic that you're trying to test. So, of course, if you take the standard deviation of the sample mean, for example, it's going to be different from the standard deviation of the median, for just to name something else. We don't have to do that in this course, fortunately, but you can imagine that if you're estimating if you're using a different statistic, that also the spread of scores from that statistic are going to change. So that's something to be mindful of. But for now, specifically this formula is the one you'll see a lot, where it's the sample mean plus minus the z star times the standard deviation of x divided by the square root of n. That will give us the confidence interval for a single mean. And also, I want to add, the methods you learn in the future are not going to be, this is just the first of many confidence intervals we will learn. And so this is the formula for this particular situation, not for all confidence intervals in the future. But what's important to remember is that every single confidence interval you learn is a confidence interval that's appropriate for a different situation. So the methods we learn later are not going to be superior to this method. It's just, well, what if you do not have a single mean and a known standard deviation? Well, what do you use then? Oh, then we have alternatives and a different formula to calculate those alternatives. So technically, this will always be the correct and best way to calculate the confidence interval for a single mean when you have a known population standard deviation. There's not going to be a better method, just different method applied to different situations. So it's helpful to think of them not as superior or inferior options, but rather to think of them as all parallel options. And your job as the researcher is to pick one that fits whatever it is that you're interested in. I'm also saying this because a lot of statistics 1B questions that you'll get, a lot of it is about understanding which method is best. They'll tell you, for example, calculate a confidence interval that is appropriate. But then you're supposed to know from the story which one is appropriate. And then in this case, if you have a known standard deviation and you're interested in a single mean and then knowing what the population mean could be, this is the right method to use. If you're in a different scenario, maybe you have two means, for example, then you have different methods for that. So that's why you want to keep this information ready. But not to go too far beyond what we're doing now. Let's have an example with this. So let's say the sample mean is 10. It's actually a coincidence. I didn't think about that consciously. And let's say we're interested in 95% confidence interval, a standard deviation of 20, and a sample size of 100. Now, most of this information you can fill in directly. And again, this is also what you would get in a question. They might not list this directly. It won't be this like bullet point-ish. They might make a story out of it, but the idea is the same, that you get this information directly, because without being provided a sample mean, and in this case the population standard deviation, and the sample size. We could not fill it in, and there's no way to just estimate it. So all this information will be provided to you directly. The only thing that's not provided to you directly is usually the Z star, because we do get told we want a 95% confidence interval, but usually you will have to look up the Z star yourself using a table. Now, in this case, when you have a 95% confidence interval, it's important to remember that it's about the middle. Have to draw it again. We have a mistake. We have a normal distribution, and we're interested in the middle 95% of scores. So this part. So didn't mean for it to make all of it yellow. Fixing my box. There we go. So we are interested in this extreme, and we're interested in that extreme. I'll use different colors just for clarity. So for this blue one, the lower bound, the only thing that's lower than it is this part of the distribution. Now, we know that we're interested in 95%, so the middle is 95%. And what we also know is that the part, because the normal distribution is symmetric always, that this part is 2.5%. Oh, 2.5%. And that this part is also 2.5%. So how much can we find below the blue line? Well, that's just the 2.5%. So 0.025. How much is below the number on the right side? 95, 2.5%. Well, that's 95, 2.5%. So that's 97.5%. So 0.975. Now, the reason I'm interested in the proportion of scores below anything is that's because what table A gives us. Table A isn't smart. It doesn't know you're trying to do a confidence interval. All it gives you is that, well, at this set value, you can find this proportion of your values below it. So drawing it always made it more intuitive to me. If we're looking for the lower bound, then 2.5% of distribution is below it. If we're looking at the upper bound, then 95 plus 2.5% is 97.5% distribution is below it. And so that's why in table A, we look up this number here, 0.975, which is gives us a Z value of 1.96, as you can see here. There, 1.96. Now, a little hint is that we also get table D, which you will use a lot more later, but for now the purpose is this at the bottom here, because table D is friendly enough to also give a row with confidence levels. So then you don't even have to think about it. You have a 95% confidence interval. Oh, cool. That's the corresponding Z star score. It's right there, 1.96. So specifically for confidence intervals, this is very convenient. Now, the reason I still explained it using this is because table D is limited. Like you only get 50%, 60, 70, 80, 90, 95, 96. Okay, that's still quite a lot, and most confidence intervals will be one of these percentages. But just in case they're trying to be funny and ask for a 92% confidence interval, with table A, you can still do it. And since you also get table A, you would have to know that you can look at this, 1.75. If you have a 92% confidence interval, the Z-score will be 1.75 and minus 1.75. And also note, by the way, we just concluded for this one, we looked up 0.975 to determine that it's 1.96. But also note, you might ask, okay, but why do we look up the 0.975 and not 0.025? Well, minus 1.96, sorry, 0.025, we look that up, then you get minus 1.96. And this is always the case. So you get the same number regardless of which of the two you look up. So another thing you could do theoretically is you look up the other one and you get the same value but just the minus. So minus 1.96 plus 1.96. If if it was a 92% confidence interval, then it would be 1.75 and also minus 1.75. So because it's always the same number, that's why you can look up either one. It's just convention to look up that one because then you get a positive number. So it's easier. But going back to our example, we now know it's 1.96 to get 95% confidence, which is great. And that gives us everything we have, everything we need to fill it in. And then we get our final result, 6.08 and 13.92. Which is to say that using a method that gives us, that includes the true parameter 95% of the time, we estimate the population mean to be between 6.08 and 13.92. And that's it. That's the confidence interval. So that's the whole calculation. So as you can see, the calculation itself is a pretty minor part of the greater idea. And the theory is important, not just for any eventual theory questions, which admittedly is probably going to be more of a numerical exam, I expect. But where the theory is also extremely important is in knowing which of the formulas you should be using. And so that's why we learn all this theory. What does it tell us? And the fact that we use this formula in this specific scenario where we are trying to have a sample with a single variable, a single sample mean, and a known standard deviation of the population. Otherwise, we might have to use something else. Now, this is a small final topic. We, generally speaking, of course, we have our sample. We want to calculate confidence interval, and it's good. But sometimes when you do research, and you can also make from a statistical point of view, if you do research, the ideal is always to have a larger sample, basically, because of course the more people you have in your sample, the better your estimates are going to be. Increasing your sample size is also the only way for a confidence interval to become narrower while retaining your confidence, for example. So from a purely statistical point of view, it's great to have a huge sample because then your estimates are going to be narrower, tighter. It's going to be better. So especially when it's extremely important, that's why you can sometimes see samples up in the 10,000s, because it allows you to make, assuming of course everything is still unbiased, that's still critical, but it gives you very narrow estimates, which is great. We like that. The problem is, however, in practice, you don't have infinite money. There are practical concerns that you can't just research something for 10 years, slowly but surely. You're going to need to post results at some point, ideally. So the trick in practice is to not just say, well, we're just going to get as many people as we possibly can, but instead, it's important to learn how to kind of estimate how many people you need to get a result that gives you the information you need. Like, how large is the effect? How large do you think the effect is, and how many people do you need to actually then find that effect reliably? And so this is part of a calculation that helps with that specifically. It's the question of how big does our sample size need to be to arrive at a particular margin of error given a particular level of confidence and the standard deviation that we observe in the population. of course, like the confidence level is something you generally don't want to touch. You have a certain confidence level you have in mind. The standard deviation of the population can't be changed because it just is the standard deviation of the population. Whatever it is what it is. Like you can wish it was smaller, but it doesn't make it so. So to have a particular margin of error, like if you really don't want to have an interval wider than 5 points, then well, better look in advance how big does your sample size need to be so that you get the width that you desire. Now, of course, samples are random, you can be a bit unlucky, etc. But actually, because the standard deviation is known. Well, anyway, you can use this method to determine what the sample size needs to be so that you get the width that you desire in the end. And it basically takes this formula and transforms it. So what happened here is essentially both sides got multiplied by the n, so that went there. Then both sides were divided by m, so m went there. And then both sides were squared to arrive at this. Now, I didn't write out all the algebraic steps in the middle, but essentially the point is that you can transform this formula into this one, but as long as you remember the final outcome, you're all good. You're not expected to transform it by hand. That's not part of the exam. It's not that interesting. So this is the final outcome that we're interested in, because then we can fill in all of this and find what sample size we need. So for example, let's say we're interested in a 92% confidence interval, a standard deviation of 8, and we want to have a margin of error of at most 2.5. Well, again, we need to convert our 92% into something else. We find, oh, the z of 1.75, because that corresponds to, well, it's the same story as above, except now it's, I'll correct it. Now it's 92. I mean, technically that also means the area is slightly smaller, but the difference is small enough that the point probably is still clear regardless. Here we have 4 and there we have 4. So we look up 0.04 and 0.96, and turns out that's 1.75. Yay, good. And so that gives us, we can fill in the formula, and that gives us an n of 31.36. And the last trick to remember here is that with sample size, we can only have whole numbers, because of course you can't have 0.36 people in your sample. It needs to be either 31 or 32. 31 isn't large enough. It's going to be, then the margin error is going to be a little bit bigger than that. So we always round up. So in this case, we would take 32. We always round up, 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 up. Right. So even if it might be intuitive to round this down to 31, but because 31 is insufficient, because it wouldn't quite be this margin of error, we would say at least 32 people to have a small enough margin of error. And so the advantage is now you don't have to randomly guess and just take a large enough sample as possible. Now you can just say, okay, I'm going to go for 32 people, and then I will get the margin of error I want, and I can make the estimate with the desired level of confidence and narrowness that I want. And that is what this formula gives us. Now you don't have to guess, you just know, okay, I need 32 people. Perfect. So I can get 32 people, I don't have to guess. I don't have to go all the way up to 100. I can just get 32, be done with it, calculate it, on to the next. Way more efficient. Right. So, is this all visible? Yes, it is, barely. So the final notes. Just want to repeat some of the core details that become that are relevant here and later. Confidence interval estimates a parameter based on a sample. That's again reinforcing what I mentioned earlier, that what a confidence interval specifically is. Other intervals do other things, but a confidence interval is taking some statistic, a sample, and then estimating a parameter based on that. If you're not doing specifically that, if you're not estimating a parameter with it, it's not a confidence interval. And 95% confidence interval creates parameter in 95% of samples to again remind you that it's the sample where the randomness is, not the confidence interval itself. So the method includes the desired parameter in 95% of samples. If the sample is biased, all the estimations are inaccurate. So if all of this, what we did here about the confidence interval and where the parameter likely is, goes out the window the moment the sample is biased, because then all of what we calculate is based on the idea that it was a random sample. So that throws everything out if it's not. We cannot calculate the probability for a random sample. We cannot calculate the probability for a biased sample because we don't know in what way it's biased. The method we learn is sensitive to outliers and assumes normal distribution as well as a known standard deviation. So this is to say, this is to remind you of the specific assumptions we made in this calculation, what we needed to fill in all the numbers, essentially, and for our probability to be accurate. Because again, we assume the normal distribution, which is, fortunately for us, usually the case. But if it's not normal, this would be inaccurate, like the interval would be inaccurate. If we don't have the population standard deviation, we can't fill in this formula, so it wouldn't work. And sensitive to outliers, it's good to remember, because we're using a mean and a standard deviation, that both of those are sensitive to outliers. So therefore, a formula that uses both of those is also going to be sensitive to outliers. Now, the thing with outliers is that it's not that it makes it mathematically incorrect or useless. It's just that it has a large effect on your results. So in communicating your result, it's sometimes worth it to highlight those outliers so you don't mischaracterize your data. A brief example of that is if you, for example, have if you take a small group of students and you want to know their average age. If you have a group of, let's say, 6 students and they're 18, 19, 20, 20, 19, 18, so the average is 19, that's, I would say, then it conveys the information well, because if you say the average is 19, you expect people to be roughly in that range, and they all are. But if, for example, you have 20, 20, 20, 20, 20, and 80, it's very old students, yes, but just something extreme like that, then the average age is 30. Is the 30 a good estimate for everyone? No, not really, because they're all 20 or 80 years old. So say the average of 30 is technically accurate, it's technically true, but it doesn't really represent the group very well, because no one is actually close to 30, but it is technically the average. So it's then better to say, okay, most people are 20, but there is also an outlier present who is 80, which drags the average up. That gives you a better idea of what's happening in that particular group of people. So this is the same applies here, where the outlier it doesn't make it technically wrong, mathematically still correct, but it's useful. It's good to be aware of it, so that when you convey the information from your sample, that you include that information. And finally, we like our confidence intervals confident and narrow. Now, unfortunately, the more confident we want to be, the less narrowness we have. So that's why we generally strike a balance, usually at 95%, but it could be a little bit different depending on the circumstances. The only way to get it both confident and narrow is with a high sample size, but keep in mind that that isn't always something you can do in practice. And that is everything you need to know on confidence intervals. So for the last few things, more of a course overview thing. As I said, most of the lectures from now will be a lot shorter because I won't need to repeat Statistics 1A for an hour before I go into the next topics. So expect the rest of the videos to be around half the size. Most topics can be discussed in an hour. So that, of course, I will just take as long as I need to talk about it. Also, it's not a hard number, but just it probably will be a lot shorter, that's for sure. That will just be from lecture 2 forward. Secondly, every lecture will also have a bunch of practice questions to practice along with it. In the lectures, I just give a bunch of examples that you can follow along with, so you can at least see it, like how it would be executed. But of course, it's also very good to try it yourself. And when I make these practice questions, the format is always that I start by doing a few questions that are very, very direct based on the material, just to make sure that the material was clear. So let's say there should be around 20 questions per lecture. So basically the first 10 roughly will just be very direct questions, just to highlight, like, do you understand that? Did you understand that? Like, just like describe this, just to prompt the memory of the most important facts that were in this entire lecture. And just to do very straightforward calculations. So it will, for example, be as straightforward as this, because the point is just like, it's not to add any complexity. It's just basically, here are the numbers. Try doing it yourself, just to see, like, okay, does that go well? That's the first step. And then the second set, so the last 10 questions, so to speak, they'll be more in the exam style, where you get a little story. You will have to just read it from the story. Okay, what is exactly happening? What am I trying to calculate? What is the correct number? What I have to fill in? So then you have something that's more closely related to the exam. And so those questions are more representative. There's still going to be a little bit of a ramp in it, where it's like we start off a little more direct and then we end up a little bit trickier sometimes. But that should give you a nice lead up to it. And of course, if you take the course and you run into any of the if you run into any questions in the meantime, then of course you're always free to alert me to it. And finally, please always feel free to message me about something. Of course, I do my best between all the videos and all the practice questions, all the content I make, to not make a mistake anywhere. But given that it's going to be hundreds of questions and hours of content, it's not unlikely that by accident somewhere I fill in a number wrong or something goes wrong. Please always let me know if you think something is wrong or if something is unclear, because the outcome is always that at least one of us will learn something. Either I was wrong, and then it's very good that you told me so I can correct it, and anyone else who reads it will be like, oh, that's good, because now they won't be confused anymore, which is always very good. Or it turned out that it was correct, and then you learn, oh, well, why did you think it was wrong, and learn about what was right, what is right. So whatever happens, at least one of us will learn. So that's always a win. So I very much welcome bringing up as many questions as you deem fit. That does it for the first lecture. And good luck with the questions, and I'll see you in the next lecture. Bye-bye.